all about gases for chapter 10. The first thing we're going to talk about is air pressure. And so you'll notice for our next 3 labs, chapters lab 5 and our lab 6 is all dealing with gases. So understanding gases really helps you with your lab unit that we're doing. So how we measure pressure. So we measure pressure with a barometer. And a barometer, and this is literally how barometers work, and we actually have one in our which is really rare. Nobody has mercury anymore. So they literally have like a bowl of mercury, and then they have a glass tube that has been evacuated of all gases. So it's kind of like took a vacuum and they sucked all the air out of the vacuum, out of the tube, and then they put it upside down in the bowl of mercury. And so some of the mercury gets taken up just based on because the vacuum it's occupying space, but the rest comes from molecules like nitrogen, oxygen, and they're all pushing down on this mercury. And when they're pushing down the pressure, the molecules are pushing down on this mercury, it pushes the mercury up the tube. And so what we call standard pressure is 760 millimeters of mercury. And it's literally like if you took a ruler, the difference between the bottom and the top would be 760 millimeters of mercury. And that's what we call air pressure. Sorry, my dogs are going nuts behind me. Okay, so hold on one second. Okay, so now depending on where you are, the pressure changes. So the way to think of pressure is you literally just as molecules hitting the side of the container. That's pressure. And so the more molecules that the higher this travels, meaning the greater the distance, the higher the pressure will be. The less molecules that hit it, the lower the pressure will be. And so that's how they measure pressure. Okay. And so what happens, and I can't even read this. So what happens to the height of the column of mercury as you climb to the top of a mountain? So has anybody ever been to the mountains or done any exercise in the mountains and it's like really hard to breathe?
Yeah, the air is thinner.
Yeah, the air is thinner, literally thinner. Or like when people climb Mount Everest to bring oxygen, because as we go higher and higher in the atmosphere, the pressure decreases. It means, and the pressure decreases because there's actually less molecules. The molecules are further away from each other. So for example, when we are down here, because we're pretty much at sea level, so about like 20% of the air is oxygen. When you go up higher, it's less air, and so it's harder for us to breathe because the air molecules themselves are further apart from each other, and therefore we need to breathe more in to get the same amount of oxygen. That's why it always feels like you're out of breath if you go up to the mountains. And when you go up to like the top of like the Himalayas, right, even less air, like there's 50%, and that's why you have to bring oxygen. So if you climb to the top of the mountain, to high mercury, what do you think? 1, 2, 3, or 4?
I had to call. I don't know, 1 or 2.
So do you think increases or decreases? I agree.
Decreases.
So will the height become more or will it become less?
Decreases.
Yeah, I'm seeing a couple on there, yes. It's definitely going to decrease, right? Because less molecules, so if I go back, if there's less molecules pushing it, that means it can't travel as far up. So it's definitely going to decrease. And look, I already canceled out 3. So the reason it is because atmospheric pressure decreases with increasing altitude. So remember, the higher we go up, the lower the pressure is. And so what about if you went to like Death Valley? So Death Valley is actually below sea level. So is the pressure at Death Valley higher or lower than the pressure we feel.
The pressure would be higher? I don't know.
Higher, yeah, so the pressure is going to actually be higher because the molecules are going to be closer together. Because remember, so if we look at like, so if we're, this is going to be, so if we look at like a mountain, it's going to be a mountain. There's like snow on our mountain, right? The higher we go up, the further the air molecules are going to be away from each other, right? And that's because, and why are the air molecules, so here's high, and then here's lower. They're going to be a lot closer to each other. And the higher you go up, the less they are. Because what's holding these molecules? Why are these molecules close together down low? Like what keeps things on the ground?
Gravity.
Gravity, yes, gravity, right? The higher you go up, the less gravity there is. And so the air molecules are further apart from each other. This is why when we travel on an airplane, which none of us get to do right now, right? This is when they travel on the airplane, have to pressurize the cabin. You know how they always say, like, if the cabin should lose pressure, right? Secure your air mass before securing another's, right? That's the statement we've all heard probably if we've been on an airplane. That's because they have to add pressure to the planes, to the oxygen in the plane. They have to add pressure, making the molecules closer together. Because when a plane is flying, which I can't draw a plane, that's going to be a plane, okay? That's a plane, okay? That's just gonna be a plane. When air molecules are so far away from each other, they're too far away for us to be able to breathe, so they have to add pressure to the plane so the molecules are close together. It's kind of like an artificial way of increasing the pressure. And then it pressurizes, the molecules are too far from each other, hence drop. Okay, if we're gonna actually use this, so there's a couple different units that we're going to need to know, and you don't really need to memorize. You'll end up memorizing a couple of them no matter what. So when we are looking at this, so it's like, what's the pressure? So if we have 132 PSIs, what's the pressure in millimeters of mercury? And so I will always give you most of these conversions. The one I probably likely won't give you is this one because we use it all the time. So 1 atmosphere, 760 millimeters mercury, or another one, we'll see in a second, is 760 torr. So these are like, they're pretty much exactly the same. Those are really the only we use. But where have you seen PSI before?
Your tires?
Yeah, tires, bike tires, car tires, right? Your car tires, like, oh, it's supposed to be between like 34 and 36 PSI. Mm-hmm. So that's what we use, like in tires. In industry, they use PSI, but in theory, we use atmospheres, torrs, and millimeter mercury. So if you're going to convert this, it's super simple. So you just use, let me just erase these. You don't need that. So you just use these conversions. So if you go from PSI to atmosphere and then atmospheres to millimeters of mercury. So you want 32 PSI, right? And you just gonna keep doing this. I give up 14.7 PSI, 1 atmosphere, right? And then in 1 atmosphere, there's 760 millimeters of mercury. So this is just like super simple unit conversions for you all. This is stuff that you've done 1,000 times. So, and then we just can't forget our sig fig starts with 3, right? Ends with 3. And when you look at this, it does, right? So if there's 14.7 PSIs in 1 atmosphere, we're way above that. And so we should have a really big number. And indeed, we have a really big number. Okay, so that's just like quick conversions. So you just need to be cognizant of what unit you're in and to make sure that you convert it to the correct unit. So that's kind of the moral of the story here. So here's all of these units. The only ones, so this here, this is the millimeters of mercury, and this is the torr. The rest of them I'll always give you, just as not like, they're so rare. So these are all the time, physics, like this is the physics ones, but we don't really use them in chemistry. And if we do, I'll always give you the conversion. Okay, so let's do PSI to KPA. KPA is just pascals. And just like I said, totally we'll give you these conversions. And atmosphere is like our base unit. So we kind of always do everything back to atmospheres. So again, this conversion is super simple for us all. At least hopefully it's super simple for us all. So if we did this, right, we would just start with 640, and then we're just going to convert it to KPA, and we do our units as we go. PSI atmosphere with KPA. And again, I'll give those to you. You don't need to memorize them. They're pretty simple. So this is just things you're going to have to do every once in a while with these conversions. Actually, you're going to do the conversions a lot. So just make sure you always have it in the correct unit, and I'll explain what that means as we go on with the chapter. Okay. So the pressure of our gas in a manometer. So a manometer is like a U-shaped tube, and you'll see this in your homework a bunch. So manometer is a U-shaped tube. And hold on one second. One second. Somebody's just loud. I can't figure out this. Okay. So, and it's kind of like a competition in between the atmosphere and the gas. And so you're going to see how one is pushing harder than the other, and that's how you measure it. And you measure the difference in the liquid level. Okay, so here's an example. This is what a manometer is. So you've got a really high pressured gas in here. So you've got your gas molecules, and they're hitting out of the container, they're hitting each other, and they're bouncing off. And a high pressure just means you have lots of molecules in air, or they're moving really quickly. And so these molecules are pushing on this mercury. Well, this is an open tube, so atmospheric pressure is also pushing on this. So these are, it's almost like a competition. They're fighting against each other. And you can hear that these molecules are winning because they are pushing this gas over here. And so you measure the difference in the height between atmospheric pressure and the gas pressure. And so when you do this, the pressure of the gas is the atmosphere plus the pressure, or so you can see here that it's going to atmospheric pressure plus the pressure of the gas, because the pressure of the gas is greater than atmospheric pressure. And so it's going to be 760, well, usually 760 plus the height. And that's the pressure of the gas. If atmospheric pressure was less than, so let's say it looked like this. So this is what it looked like. That means that the atmospheric pressure is actually greater than the pressure. So then you would actually subtract it. So in homework, you're going to practice that a lot. So what you're looking for is you're looking for who's winning. If the gas is winning, that means that you're going to have to add 760. If the atmosphere is winning, then you'll subtract 760. Okay, so if we look at these properties of our gases. So if you, in this chapter for the next few weeks, the thing is to make sure that you're always thinking about the gas like at a molecular point of view. Like, how is gas behaving? Because that will help you answer the questions. The hardest part about this next section is the qualitative, not the math part. It's all about the concepts. The conceptual part of this next chapter can be a little difficult, but if you think of it as an actual, look at it as a molecular view, like how are the molecules behaving, it makes it a little bit easier. So gas molecules expand to fill their container. They always take the container. They have a very low density. So remember, density is, right, mass, volume. Their volume is gigantic and their mass is tiny, so it makes a very low density. They're very compressible, right? So you could take all of the gas in the room you're in right now and probably compress it into like a coffee cup. The mixtures of gases are always homogeneous, meaning they mix completely and thoroughly. And they're fluid, they move. Okay, now this, I think kinetic molecular theory is one of the best ways to understand the movements of gases. So they're constantly moving. And we assume, this is an assumption we make, that the attraction between the particles is negligible. That means they're neither attracted nor repelled by each other. So they're almost like independent pieces. Think of it a little bit like pool balls on a pool table, right? They go by each other and they have no attraction to each other. They're also, when they hit another gas particle or the container, they don't, but they bounce off and continually moving. So think of it as like a pool ball, but if you were playing pool with bouncy balls. If you're playing pools with bouncy balls, and when they hit each other, they just bounce right off each other, right? And if they hit the side of the container, bounce right off it. So it's kind of like, you get a pool ball, but with like bouncy balls. And that's kind of like how gases behave. So they have no attraction, no repelling of each other. They're completely ignore each other. Their collisions are perfectly elastic. That's like a bouncy ball, right? They just keep going and going and going, and they don't ever lose any. And if they hit the side of the container, they just bounce back. If they hit each other, they just bounce back. They're mostly empty space. So there's mostly empty space compared to the particles. And the average kinetic energy of the gas particles is directly proportional to the temperature. So it's directly proportional to the temperature. So if you raise the temperature, you raise the speed. Let's see here. You've probably experienced this, right? So if you have like a water bottle or a soda bottle or something of the sort, and it gets warmer, when you open it, you hear that sound, and that's the gases escaping. That's because we've sped up the gases, so now they're pushing against the container harder. So the higher the temperature, the faster the gas molecules will move. So if you raise the temperature, the average speed increases. Now, they don't move at the same speed, but the average speed increases. So remember, if gas molecules are hitting the side of the container, right, that's our pressure. Pressure is just the molecules hitting the side of the container. If you increase the temperature, that means we have more molecules hitting the side of the container, which increases the pressure. Right? So for example, if you had a soda bottle, if you had a bottle of soda, and you left it out on the counter, right, you would hear a big shh, right? Because the pressure inside of the bottle had increased because you increased the temperature. Now versus if you let it in the fridge, the molecules are now moving slower. So they're still hitting the side of the container, but there's not as many hitting the side of the container. So the pressure would decrease.
We didn't have those last slides. Is that fine?
Can you not?
That's third slide. We don't have it.
They just weren't on the actual printout of the notes.
Oh yeah. Yeah, I skipped those.
Oh,
So sometimes, yeah, I just
skip
updated
them.
this
We don't
one.
need to know that.
Yeah, it's
Oh,
pretty
we don't
easy.
know it?
Hopefully, right? Okay, so because the gas particles are constantly moving, they're always hitting the side of the container with a force. So remember, whenever you think about pressure, you just think of a container, and it's the molecules hitting the side of the container. That's how to think about pressure. More molecules, more pressure. Less molecules, less pressure. If you increase the temperature, the molecules are going to hit the side of the container more often. If you decrease the temperature, the molecules aren't going to hit the side of the container as often, meaning less pressure. So if a lot of particles in a gas sample, that means that they're going to exert force and the pressure around them. That's what we call our constant pressure. It's just molecules hitting the side of the container. So that's our container. This is the molecules hitting them. So molecules hitting the side of the container, that is what pressure is. Okay, so now when we look at the kinetic energy, so kinetic energy is just energy movement, right? We're talking about the movement of the gas fields. It depends on the average mass and the velocity. So this is a physics thing. We're not going to be doing any math with it. You just need to think this qualitatively. So this is kinetic energy. Here's mass, here's velocity. So it depends on mass and velocity. So gases at the same container obviously have the same temperature because they're in the same container, and therefore they have the same average kinetic energy. So the gases that are in the same container, so if I have two gases, there's one gas, it's going to be really small. We'll call that one hydrogen. And then we have another gas. This gas is a lot bigger. Big giant gas. Now, because they're in the same container, they have the same kinetic energy. But does that mean they're moving at the same speed? So say my left arm and my arm equal in strength. And in one of them, I threw a bowling ball. The other one, I threw a ping pong ball. Now I'm throwing them with the same amount of force, but will they move at the same speed?
No.
Definitely not. Same with these gases. Have the same average kinetic energy because kinetic energy is based on mass and velocity, right? So if you have a really, really heavy molecule, it has a big mass but a low velocity. Same kinetic energy. If you have a really, really light molecule, it has a really low mass but a high velocity. So it all equals out to the same kinetic energy. So even if they're different masses, they have the same kinetic energy, but they have different velocities. They're moving at different speeds. Lighter particles will always have a faster average velocity. Lighter particles will always move faster than big particles, but their kinetic energy is the same. And that's why you'll often temperature is proportional to kinetic energy. If you increase the temperature, you increase the kinetic energy of the molecule. If you decrease the temperature, you decrease the kinetic energy of the molecules. But again, they're not moving at the same speed because of the different masses and volumes, but you have the same kinetic energies. So here's what we're talking about with the speed and the molar masses. So sometimes this can be a little like tricky. So now it's important to know that if all you have is hydrogen in like a container, the hydrogen molecules aren't all moving at the exact same speed. Some will move slower, some will move faster. But in general, so if we have all of these, here's the molecular velocity, and this is just the relative numbers of the molecules, so these are all going to be at the same temperature. In general, hydrogen molecules are moving faster than, we'll just compare to oxygen molecules. It's because they're lighter, right? So there's lighter, and again, this distribution, just all molecules don't move at the same speed no matter what. But you can see, in general, these hydrogen molecules are moving at much faster speed than these oxygen. So if we had to like say the average speed of hydrogen, I don't know, right? Maybe around here, that's where we could like average that, where oxygen speed's down here, right? So around like 250-ish versus like 1700-ish, right? Meters per second. So now their kinetic energies are the same, right? Hydrogen's kinetic energy is the exact same as oxygen's kinetic energy, but hydrogen is moving faster than oxygen is. So it's really important that you don't mix up the two concepts of velocity or speed and kinetic energy. The kinetic energy of any molecule at the same temperature is exactly the same, but they're moving at different speeds. So this brings us to temperature and molecular velocities, how you can actually calculate this. So as the temperature increases, the molecules will be moving faster. Oops, so if we go with this. And so here's kind of the formula that we use here because it makes our life easier. This is just for and this is just, this is like our velocity, our molecular velocity, that's what we call this. The only thing, so for this one right here, if we use a smaller mass, this R is a different R. This R is 8.314 joules per mole. So, oh, here's right. We have a new R. And so we need to remember this new R here. And then also with our molar mass, you're going to see here, it's in kilograms per mole. So this is speed, and we'll do a couple of practice of these so you can see how this works. Okay, so remember all molecules are traveling at different speeds, but they all have kinetic energy. And this is what we were talking about, the root mean square. This is just kind of like how we calculate the average velocity. So a lot of people don't like to use velocity speed. They're a little bit different, but for our purposes, it's fine. It's not physics. This is just our average velocity. You're never going to have to do math with this. Just know what this is, that this is our root mean speed, or root mean square. So this is just what we call a Boltzmann distribution. So this is, I don't know, this is just oxygen, temperature is 300 K. Not every oxygen molecule moves at the same speed. If we took our average, right, this would be, so our averages would be the average. And this is what we're talking about. This is how you would calculate the average using that formula, which we will not actually have to do. You just need to understand the concept behind it. I'm not going to ask you to do the math with it. And so this is temperature versus molecular speed again. So as the temperature increases, velocity increases. And so it actually, what we call, you'll see it spreads out. So this is all the same molecule. So this is nitrogen. So if you have nitrogen at 273 Kelvin, you can see the distribution of it right here. It's a little tighter, but as we heat it up, it kind of spreads out. But you can see at 2000 Kelvin, nitrogen in general is moving at a much faster speed, right? The velocity is much higher at 2000 Kelvin than it is down here at 273 Kelvin. Okay, so let's do practice with this one. So we're gonna do the root mean velocity of methane at 25 degrees Celsius. And so this is what I was talking, this is this RMS. And so when we do this, this is like a little bit different than I showed you, hence you'll see why. It's because I'm correcting for our units. So super important here, super important things about gases. Number one, gases always have to be in Kelvin. Always, 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 always. If I ask you a question and I give you Celsius, and it's multiple choice, and all the answers is in Celsius, you have to go from Celsius, convert it to Kelvin, do the problem, and then convert it back to Celsius. You can never, ever, ever, ever do a gas problem with Celsius. They all have to be in Kelvin. So always remember, convert to Kelvin. Add 273.15. Okay, so here's, when we see here's our 3, here's that special R. 8.314. So we're like, why do we have to use 8.314? Okay, here's our tiny bit of physics here. This is equal to 1 joule. So in physics, that's the definition of a joule. So what we do with our 8.314 is we just say R is 8.314 joules per mole K. That's okay. And so that's why we use this. And the reason that we have to put this in kilograms is because of this kilograms. So the only tricky part about this is you need to remember that you put your molar mass. So you just move your decimal, just do it. See what I did here? I just said times 10 to the negative 3. So you can either move your decimal or just make sure you correct for kilograms instead of moles. And so then your units are going to be meters per second when we do this one. So we cancel out all of ours. And so that's how our velocity works, how we calculate this. So you just find your mass. Find your mass, multiply it by 10 to the negative 3. Don't forget that R is 8.314. Don't forget this temperature has to be in Kelvin, and then don't forget the 3, and then you take the square root of the whole thing. So that is our root mean square velocity. Okay, one more quick thing. Diffusion and fusion. So diffusion we know really well. So diffusion is just molecules spreading out from a high concentration. So for example, if you were in your room watching your chemistry lecture and someone lit a candle in another room, the smell of the candle would diffuse over the entire house. So we're very familiar with diffusion. Effusion is a little different. Effusion is molecules going through a small hole into a vacuum, technically diffusion. So sort of an example of effusion, this would be like, do you know those like the balloons, like the normal balloons you get at like Party City, right? They always deflate in like a day, right? The regular balloons. Or you can get like the shiny metal mylar ones, like tiny ones. Those last for like ever, right? They stay up for weeks. It's because the normal balloons we have a lot of tiny little holes in them. So the molecules, right, the air molecules they put in them effuse out, right? And then they sink, where the helium can't get out of the shiny metal balloons, right? Because they're the holes in the metal balloons are much smaller, and that's why they last a lot longer. And so that's kind of an example of effusion. So effusion, technically it's into a vacuum, but it's movement of a gas through a tiny hole. And so the rates of these are both related to that root mean square average velocity we talked about and the mass. So remember, for gases at the same temperature, right? We just looked at it, it's proportional to the square, the inverse rate to the square of its root mean molar mass. And remember, at the same temperature, they have the same energy, but they're not moving at the same velocity. So here's an example of effusion, right? It's like movement through a tiny little hole. Just so you can see this one, like tiny little hole, that's effusion. So this brings us to Graham's law of effusion. So if you have two different gases at the same temperature, right, that means they have the same kinetic energy. The ratio of their rates of diffusion is this equation. Okay, so this is not a particularly difficult equation, but it is a little tricky. So you have to think of your answer before you actually finish your problem, and I'll show you what I'm talking about. So it's just the molar mass of B, and then the rate of B is here, molar mass of A, and then gas A is here. Now the question is, where does A go and where does B go? You just need to remember that they go on opposite of each other, and then you need to think about your answer. Now, what do I mean? Okay, so for this question, we have a rate of an unknown gas, and so it fuses at a rate of 0.462 times nitrogen. So does that mean that this gas is heavier than nitrogen or lighter than nitrogen?
Heavier.
It's heavier than nitrogen. Yes, this is what I mean when I talk about how you have to think about your answer before you do it, because Graham's law is kind of tricky in this way that I'm going to show you. So you need to go, is my answer going to be bigger than or smaller than, right? Is my molar mass bigger than or smaller than? This molecule needs to be bigger than nitrogen in the end. So if we use Graham's law, here molar mass of nitrogen. And so when we plug this in, again, like where are we going to put nitrogen? Are we going to put it on the top or the bottom, right? Because we have our rate, and then we nitrogen. This one's a little easier because it's automatically, right? If you just one over here, it's automatically on the top, which means nitrogen has to go on the bottom. So if we do this and you solve for it, you get 131 grams per mole when you solve this. Now, this is greater than nitrogen, but it is just as easy to solve it the wrong way and get a number smaller than nitrogen. If that happens, you just need to flip your numbers. Now I'm going to show you an example of what that means. So calculate the rate of effusion for oxygen to hydrogen. So oxygen to hydrogen. So should oxygen move faster or slower than hydrogen?
Slower than hydrogen.
Yeah, oxygen is heavier, so therefore oxygen is slower. So if you're going to get a rate, your answer should be less than 1, right? Because oxygen should move less than hydrogen, so therefore the rate should be lower than 1. So if you solve this, so the question is, it's rate of gas A or rate of gas B. What does gas A and gas B do? So like, for example, So if I did hydrogen to oxygen, you could do that. But you also, I mean, you could have put an oxygen top or hydrogen on top. But you also could have done rate hydrogen over rate oxygen. It's just going to keep doing this. And if you did this, you have molar mass of oxygen over molar mass of hydrogen. You could have done that. You could have done that. Absolutely. Like, how do you know which one it is? It's kind of like it just depends on the problem. Now, either of these is the correct way to write this problem. But on one of these, you're going to get the answer, and this is an incorrect answer. You're going to get the answer of 0.25. If you set it up like this, you get the answer of 4. So then, either of these, so you would have either gotten 0.25 or you would have gotten 4. But then in the beginning, you need to remember, the question was oxygen to hydrogen. Oxygen is heavier than hydrogen, therefore it should move slower than hydrogen. If your answer was 4, that means you're saying that oxygen is moving 4 times faster than hydrogen, which is not possible. So then you have to go, oh no, I flipped my answers. So you would have had 32.0 over 2.016. So you need to go, oh no, I need to flip my answers. And then you would have gotten 0.25. And then that does mean that now oxygen travels at 0.25, 25% less quickly than hydrogen does.